Hello everyone, welcome back to another Rated Powers webinar. First of all, thank you all for joining. It's always a pleasure to have so many people from the industry checking these interesting topics out. And before we start, I would like to highlight one webinar that we have in the following weeks. Let me just show it to you. You can access it from RatedPower's website. Here you have access to all the webinars. And this one, for example, is the next one that is very interesting. Prism centralizing data for smarter renewables, site analysis and prospecting. It will be very interesting. So I encourage you everyone to join and check it out. And again, let's just wait just a few more seconds for everyone to join before starting. Okay, and the topic of today's webinar is balancing the grid and the role of battery energy storage systems in ancillary services. We've been listening a lot about batteries in the last years, and we see a tendency towards this strategy or towards this technology in the future. So it's very interesting to start digging deep into different strategies and functionalities of this technology. So a bit of myself. My name is Álvaro Benito. I'm a senior software engineer at RatedPower. I've been working on the company for around 4 years already, specifically in the interconnection team. I've been working on substation, transmission line, and grid compliance. And now we're going to cover a bit on how batteries can work within this grid compliance and grid stability. And for this, I have prepared this presentation with the following index. So first, a small introduction on what ancillary services and grid stability is. Then some types of ancillary services, the most common are them and the most important ones. The role of batteries for these ancillary services. Then we will go a bit deeper into specifically frequency regulation, which is the main objective of batteries or the primary target for ancillary services with batteries. Then we will look a bit into future trends of this technology. And then we will have an overview of what happened last month in Iberia with the blackout. Many of you will already know that in Spain we had a blackout. So we will be covering a bit on whether BESS would have been useful for this case. So to begin with, a small introduction here, and I would like you to present the concept of grid stability. And grid stability basically refers to the power system ability to do two things. The first one is to maintain a constant frequency, voltage, and power flow equilibrium. This means that here in Europe we have 50 hertz, for example. So the target is going to be to work around this 50 hertz. That's the first objective of this grid stability. And the second one is to recover quickly from disturbances. So if there's a fault in a transmission line or in a generator, the grid should be able to stabilize using like different generators or different services to reach this equilibrium back. And here is where ancillary services come in place. So ancillary services are the tools that allow the power system to recover from these disturbances and to keep this equilibrium. And I want you to understand the importance of these services through an example. So this is the chart of frequency during an outage between French and Spain interconnection in the 24th of July of 2021. This happened because of a fire. So you see in July, really hot summer. So because of a fire, France and Spain lost around 2.5 gigawatts of power because of an outage in a transmission line. This resulted in a big drop of frequency in the Spanish part and a slight increase in frequency in the French part. And here is where FCR, which is frequency containment reserve, and load shedding, which is basically just cutting some loads. So, for example, pumping power plants would stop pumping water in order to reduce the load. So these ancillary services came into place and they helped recover the frequency back to normality. After around 40 minutes, 45 minutes, Iberia was able to reconnect to the European Union, and we reconnected the France and Spain connection. This is why you see a small transient there at the end. And all of this was achieved thanks to all of these ancillary services, and nothing was noticed at the consumer level. So now let's go a bit into types of ancillary services, and we will be highlighting four of them. The main four of them are frequency regulation. This is just keeping the frequency stable at 50 Hertz in Europe, for example, 60 in the United States. And this is achieved by adjusting the active power. So if we increase the active power, we will increase the frequency. If we decrease the active power, we will reduce the frequency. Then voltage and reactive power control. Same idea, we'll be regulating voltage through reactive power, so injecting or absorbing. Then operating reserves, which provide backup power for sudden imbalances into the grid. And finally, black start capability, which allows to restart the grid after a blackout. And I would like to focus primarily on frequency regulation because it's the primarily used case for batteries. And here we have four, well, according to ENTSO-E, we have four definitions. We have primary reserves, or FCR, secondary reserve, or FRR, a tertiary reserve or manual FRR, and replacement reserve. And I will go a bit into detail now. So the first one, the primary reserve, is the frequency containment reserve, according to ENTSO-E. The objective of this is to contain the frequency immediately, so that the big drop that we saw before, this FCR will just jump into place and try to contain this frequency drop. It's very fast. The full activation is achieved at around 30 seconds, but it starts providing services almost instantly. It can work up to 15 minutes. It gets triggered automatically. Otherwise, I think humans are not as fast to react to this. And it takes a part in the capacity market. Then we have the automatic frequency restoration reserve. So if the primary reserve's objective was to contain the frequency drop or increase, this one tries to restore the frequency to its nominal value. It's a bit slower, so the full activation takes around 5 minutes. It can operate until the imbalance is corrected. It's automatically triggered through a TSO signal, through software and algorithms that they have. And it typically is part of the capacity or energy market, depending on the market specifics. Then we have manual frequency restoration reserve. So this is the tertiary one. The objective is to replace the secondary reserves. If there's no more secondary reserves, then this will come into place. It takes a bit longer to activate, between 12 to 15 minutes. Again, it can operate continuously as needed. This is also triggered manually by the TSO. So typically through the SCADA systems or just a phone call before. And also depending on the market, it can be part of the capacity or the energy market. And finally, we have the replacement reserve. The idea here is to replace all the FRR and FCR that have happened before. It takes longer to activate, normally 30 minutes, but it can be a bit faster. It can be operated for a long period of time. Also automatically activated, well, manually activated by the TSO, and it's typically part of the energy market, or there are some ad hoc separate contracts for it. So this is for frequency regulation, and now let's see what is the role of batteries in all of this. So for voltage control and reactive power, long story short, batteries typically cannot compete in terms of price with capacitor banks and statcoms. So there will be virtually no projects where the main objective of a battery system is to have voltage control. Then for black start capability, there are some limitations for batteries. First is that they are not able to provide like large short circuit current, so they have low short circuit current. This is interesting because large generators might require to have like a high short circuit current to turn back on. They are also less cost effective than other solutions, and finally they are less reliable and they have limited energy availability. So in terms of like in periods of crisis, typically pump storage is used or diesel generators. Finally, operating reserves. Again, batteries suffer from the same issue. They have limited energy availability, typically 1, 2, or 4 hours of operation. They are less cost effective than other solutions. And then there's the opportunity cost, because if you have to keep certain energy for the operating reserves, then you are not using it for other markets, which might be a lot more lucrative, such as arbitrage or peak shaving. And just for you to understand the usage of batteries, this is from the US from 2023. In green, you see the capacity available of all the batteries installed in this year. One battery system can provide different strategies or different services. That's why you see that if you sum all the green charts, it will go way above 100%, because you could have a system that provides arbitrage and frequency regulation. But mainly here, I want you to understand that the main two objectives of the batteries in the US right now is arbitrage and frequency regulation. We see here that spinning reserve is also provided by a lot of them. And also we see a big importance in wind and solar penetration. So this is why co-located renewables and excess wind and solar is also important. If we check the purple ones, which is the primary objective of the battery, so this means each battery system will have a primary objective. We see that arbitrage and frequency regulations are the two main focus of battery systems, and also co-located renewable and excess wind and solar is gaining importance. For example, spinning reserve, even though many batteries can provide this service, almost none of them is primarily focused at this service. So now that we know that batteries' main focus is frequency regulation, let's move on to why and how we can leverage and study this. And there are three main reasons. First, batteries are really fast, so they can jump into FCR, which is typically a more lucrative market. So very fast response. They ramp up almost instantly, so they have you can be at nominal power just like clicking a switch. Of course, it's not as simple, but they are very fast to ramp up to nominal power. And also they can balance both supply and demand. So they are very flexible for over frequency or under frequency cases. I want to present a really easy and simple way to study the frequency capabilities of a BESS plant. So this is the well-known frequency droop control. So given this PF chart right here, we have to define what we call the non-critical frequency window. This is a window where the battery system will not do anything. It will not charge or discharge. We don't want it to turn on and off constantly just by really, really small deviations. So we have to define this non-critical frequency window. Then we have to define the maximum and minimum frequency window. In these windows of operation, we will ramp up or ramp down the generation of the batteries linearly, depending on the frequency deviation. By the way, these operation limits of 49.98, 50.02, or 50.2, these values are based on the NSOE. And finally, we know our curve of operation, and we need a time series, a grid frequency time series provided by the grid operator. This is in order to simulate a real case scenario and check the capability of our battery system. So the idea would be to, like, given this information, we will be able to simulate with different combinations of installed power and capacity using the frequency time series from the grid operator. So it will be very simple. Every time stamp, we will just get the system frequency, check if we are outside of the non-critical window. If we are on, the battery system allows us to charge or discharge because we could be at the maximum or minimum charge. Then we will charge or discharge to the grid. By running a time series analysis, we can check whether our our battery system is able to provide with frequency regulation throughout the whole provided time series. Now, of course, this is very simplified. We would have to include round trip efficiency, conversion losses, degradation, some economic variables such as capex, opex, and revenue, and to combine other services such as arbitrage, peak shaving, etc. And now let's see a bit into future trends of this technology. Here I would like to compare the situation of batteries in the US in 2017 against what we have right now. I think this is a good way to see the tendency. So this is the capacity available for different services. So it means that, again, one battery system could be providing different services simultaneously. And we're comparing 2017 to 2023. So as we can see here, we see a shift towards arbitrage. So it went from 44% around that value to 72% or 71%. Frequency regulation also increased a bit, but we don't see something very significant. We see also a very big increase in excess wind and solar. This is thanks to renewable penetration. And finally, also we can see that for blackout start backup power, batteries went down. So I guess we are tending towards other solutions. So it's very interesting to see the landscape of what is going on in the US, and maybe we can also relate this to other places. Now for 2023, this is comparing the installed capacity against the proposed capacity for future projects. This is the primary service, so this means that it's the primary target of the battery system. So each battery system will only have one primary service here. And again, we see a shift towards arbitrage. We are seeing an increase for like 49% to 39% to 49%. And we see that frequency regulation, despite being still important, it might not be the most cost-effective solution or the most lucrative out of all of them. So yeah, we see a tendency towards arbitrage, and that's what we're seeing also in general in Europe. And now I want to highlight some of the challenges for integrating these battery systems for ancillary services. Sorry. First one would be the increase in renewable penetration. So this is kind of a double-edged sword because we know that there's a lot of uses in batteries with renewables, but at the same time it makes the analysis of the projects a bit more complicated. So it makes everything a bit more complex to think I lost the share screen. Let me just, okay. Then we have market saturation of ancillary services. So you cannot just put gigawatts and gigawatts of frequency regulation. Eventually, it will become less and less attractive in terms of cost. Then a shift towards mixed strategies is very challenging. Trying to study both arbitrage and frequency regulation and voltage regulation all simultaneously, having these many options makes it very complicated to find the sweet spot or the optimal in terms of economics. And finally, the regulatory barriers. I think this one is the most important. There are a lot of countries where there are not any grid codes defined yet, so it's very complicated for developers to deploy any battery systems in these places. And this is the part of the theory. And now let's jump into what happened last month in Iberia. This is a really hot topic. First, I would like to do a disclaimer here. The topic is still in investigation. There's still a lot of unknowns. Probably the fact that this is also affecting politics makes it a bit slower. So here I will just try to share what happened and try to give some insight of what I found out in general after some well, after checking with some experts. And the first thing that we have to notice is that this is obtained, by the way, from Grid Radar, that before the blackout, around 10 to 15 minutes before the blackout, we observed some interregional oscillations in the frequency. There's nothing that proves that this is related to what happened, but it is very suspicious that like a few minutes earlier before the blackout, something like this happened. So that's a first interesting thing. And then we will move on to what really happened. So again, this is obtained from Grid Radar. This represents the frequency during the blackout. And the first thing that we can observe is that at 12:32 and 57 seconds, we had this drop in frequency, and this was produced by a generator loss, something that can happen, and the network was perfectly prepared for this. We see that the frequency dropped, but then immediately frequency containment reserves jumped into place, and the frequency was contained at around 49.95 hertz. However, this frequency, instead of like going back to normal, it went down a bit, but it still was within reasonable levels where other generators shouldn't have failed. However, 20 seconds later, around 20 seconds later, we had another generator loss, and then this led to a cascading effect of losing even more generators, frequency dropping down even more and more, and it went down to, according to ENTSO-E, to 48 hertz. Then another interesting thing that happened, you see here that in Malaga and Porto, both in Iberia, frequency dropped like really low. However, in Pega and Belfort, despite having a drop, it didn't go as bad. This is because at 10:33 and 20 seconds, Iberia disconnected from Europe. So Europe started stabilizing, and Iberia just went even worse. Now, the question is like, what would have been the impact of batteries in this blackout? And the first question that arises is, would batteries have helped during the blackout? By the way, this is just all my personal take, so don't take it as the reality. It's just my personal opinion. And I do believe that batteries would have helped in this case, definitely. In the end, they could have been able to inject active power, and they could have been able to help recovering um, the grid. However, would they have been enough? Well, that's an unknown. We don't know. Maybe even by placing gigawatts of active power from the batteries, it wouldn't have been enough, because the last question is that we don't know what caused the generator loss. We're assuming that it was the frequency drop that made other generators just disconnect. It could be a rock of protection tripping, so rate of change of frequency protections. It could be due to a phase angle difference with Europe, for example. It could be caused by over voltages. There are some people reporting over voltages a few seconds before the blackout. So we don't really know the cause, and without knowing the cause, it's very bold to assume that battery systems would have been able to prevent this issue. So until we know what happened, what really happened, everything is just opinions. So yeah, we will see about this. And without further ado, we can jump into the questions. Thank you everyone for attending. I see that it has been a very active webinar. So yeah, feel free to place your questions in the box, and I will be happy to answer them. Okay, so first question from James: do lithium ion phosphate represent the best and most affordable option on the market currently? And what changes do you see coming into the market in the next few years that could reduce cost per megawatt hour? Okay, so I do believe that lithium ion offers really good high efficiency and energy density. I've seen some sodium ion batteries that are very promising, because also sodium is very abundant, but it has lower energy density and it's very early in commercialization. That could be an alternative. Flow batteries, I think, are also there. They probably will be more related towards long-term storage, so probably not for ancillary services. So yeah, I think right now and in the following years at least, lithium ion will still be the best and most affordable option. And also there's the technology of scale, like the economy of scale, which makes them cheaper. So we will see, but for now I would say that lithium ion is still the predominant solution. Okay, so there's another question. Are there any plans to include this in rated power? So right now we are looking, like, in the short term, I would say no. In the following months, we are studying still what we want to do, but it's in the roadmap in the midterm to check how we can implement batteries for ancillary services. Right now, we already have the arbitrage, so you can like input prices and then simulate with these prices. But yeah, for ancillary services, not yet, but it is within the expected roadmap. Okay. What would be the difference between short duration and long duration BESS? In your view, which would be more convenient for Spain? I think this depends exclusively on the project. What I've seen is a tendency, well, also based on the US. So honestly, based on the Spanish market, I wouldn't know. But in the US, I saw a tendency towards 3 hours of operation as the average. So between 2 and 4 in general. And what I also observed, so what I also observed is that previously in 2017, most of the projects focused at frequency regulation were targeting like 1 hour of operation, something like that, because you want high power and you don't really care about the capacity. But lately, even frequency oriented projects are targeting also 3 hours of operation at average. And I think this is because they are always mixing arbitrage with frequency regulation. So this is what I have seen as the tendency. I believe long duration batteries are still something that need to be worked on a bit. Because yeah, most projects that I see are a lower duration. But yeah, it would be interesting, I think, in like if we want to have like a fully renewable landscape, it would be necessary to have long duration battery systems. What is arbitrage exactly? So arbitrage is basically leveraging the difference in prices. So there are like during the day, some parts of the day will have really low energy prices. So at that point, you will charge your batteries, and then when the prices are higher, you will discharge your batteries. And it's basically utilizing this gap in prices throughout the day to make profit. Okay. What can the national grid operators do to prevent the Iberian situation from happening on such large proportions? I think it's very hard to answer this because we don't really know what happened yet. So without knowing what the reason behind this blackout is, it's very hard to give a solution. I've seen some people claiming that maybe the grid codes are not strict enough with regards to PV penetration plans. Uh, but again, it's something that we don't know yet. After we know the reasoning behind the blackout, it will be easier to know what to do. But it's very, very hard to know that. Okay, there's another question. Well, what will be the life cycle of batteries? For the future, I don't know. I know it's well, depending on the service, of course, and the number of cycles. You could have like 15 years, also depending on the technology. If you are more aggressive and do more cycles during the day, like 2 cycles, you will have less cycle of life or life cycle, sorry. If you are less aggressive and you do, for example, 1 cycle per day, they will last longer. But yeah, for the future, I know that flow batteries, for example, they claim that they can last almost indefinitely. So that would be a really interesting technology in the future. But for now, yeah, around 15 years, more or less, depending on the usage. Okay. Macroeconomically speaking, what is your opinion? Would be better to use nuclear or to have huge deployment of batteries to control the frequency at country level? Um, I think both solutions are not excluding the. I do believe the like grid forming inverters and inertia provided by inverters is something that can help out. Although I know that it's not exact, it doesn't provide all the benefits of the inertia provided by huge generators. Me personally, I am not against nuclear or anything. I think we can reach a, a base load of nuclear plants, but I also do believe that batteries can come into play. So yeah, I don't think there are excluding solutions or that one will take over the other. They have different different targets. So yeah, I think both can live together. Okay, so I don't see any more questions. Okay, so I think we can leave it here. Thank you everyone for attending. It's a really interesting topic. If you have any other questions, feel free to reach me out or anyone from RatedPower. Here you have my contact. So yep, I think we can close it here. Thank you everyone, and have a nice day.